Hi everyone, I am Ivor Duvenacher and I will be running through the mechanism involved in the synthesis of Calix for Pyrrole, which is this macrocyclic compound here consisting of four Pyrrole rings and some dimethyl bridges. Alright. Before we jump into the mechanism, let's just quickly have a look at the schematic overview so that you know what are our regions and our catalysts. We have pyrrole and we've got acetone. Then we also have sulfuric acid as a catalyst, and that's all. That's really all. The other stuff is just solvents and more equivalents of the same thing. In this reaction, you will get four possible conformations. With other words, your product can look four certain ways, and you can justify or confirm this via spectroscopy results. So let's quickly just look at the four possible conformations that your product can get. It is the 1,2 alternate or the 1,3 alternate, the cone or the partial cone. Now let me just get my pen here. Let's use this one. So if we look at the each drawing here, then you will note that some is red and some is green. The green ones are facing towards the center of the cavity of the microcyclic compound, whereas all the red pyrrole rings are looking away from the cavity. So if we then look at this 1,3 alternate and we draw a line here through the center, it's symmetrical. If we draw a line here, it's symmetrical. Doesn't matter where you draw this line, it's just always going to be symmetrical. The 1,2 alternate, yeah, you can draw a line like this and yes, then it is symmetrical. But if you draw a line like this, it's extremely unbalanced because now you've got two pyrrole rings looking towards the center of the cavity, and they are sterically hindered now. There's a lot of bond, what do you say again? Bond strain. There's a lot of strain there. Now, to explain to you the other two conformations, let's just delete this. To explain to you the other two conformations, this cone conformation is actually a product of a product. With other words, if you get the 1,3 alternate, then that will be your product, but you might be instructed to add hydrogen fluoride. There we go. And when you add hydrogen fluoride on your product, you get the cone formation where fluoride acts as an ion, and then it draws all the nitrogen groups on each pyrrole ring towards the cavity of the ring in the center. So in the real world, this fluoride ion, which is now functioning as an ion, would be here, down here in the middle, where it's going to be closer to the nitrogens. I just drew it up here for you to see how it pulls, all right? But in reality, it's not really that far up. There's nothing pulling that fluoride ion up there. It's going to be down there. The partial cone, this is not something you're going to see. It's very uncommon, very unlikely. Your product is most likely going to be the 1,3 alternate. This is the most stable, the most thermodynamically favored, and as such, that will be your goal. So let's move on. Yeah, here I just tell you this will be your product because, you know, this is the most stable, nothing to see here. And we already discussed this. Note though that this is not your product. This is just a spectroscopy comparison for your product, okay? As long as you understand this, you will understand the mechanism. So let's jump into the mechanism then. So just a warning, we're going to start by going through this mechanism really quickly, and don't be overwhelmed by it. All right, just bear with me. There's going to be a time where we're going to go through this mechanism step by step by step by step. For now, I'm just going to discuss the outline of the mechanism, and then afterwards we will go slow and you will be catching up on how this mechanism works. So don't be freaked out if I skip my slides too soon for you, okay? We're really going to go into deep detail. So here is the mechanism. It starts here on the left top, and that starts with an acid catalyst being deprotonated, and then it goes around. Let me show you how it actually goes around. It looks like a downward spiral staircase, if you will. So this is our last step here, okay? Then it's just rearrangement, and then it makes this product, and then you add hydrogen fluoride, and you will get this, maybe, if you have to. So now you can see I highlighted for you, this is your actual product, and then here I highlighted for you, this is your spectroscopy result comparison. Alright, so this mechanism goes through only 4 steps. Basically, if you're going to get an exam, and if this mechanism is something you need to know, then all you have to do is just memorize 4 steps. And these 4 steps will repeat itself all the way to the end in this sequence. And then you would be able to draw the mechanism without really studying too hard. We've got 4 steps. It is protonation, nucleophilic attack, then protonation again with water as a leaving group. Wait, I drew it at the wrong place now. All right. Don't look at this. Don't look at this. I'm so sorry that was there. This is not the protonation step, but there is a protonation step that is there. And then we got elimination. This is what I tried to draw here, was elimination, okay? Protonation is this, and it's going to be very similar for that. I just draw the wrong molecule there. I'm so sorry, that's so stupid of me. Here we see the full mechanism, and we can go into detail now. Let's zoom in, and let me show you how this goes. Okay, I'll go a little bit deeper. Go here to the top. Yes, I think this is good. Let's start at the beginning. So, at first, this is where we start. We start with the protonation step. Then, with the nucleophilic attack, we will go into detail why the attack looks like this. Then here's our protonation step that I didn't draw last time. I'm so sorry about that. This is how it actually looks like. Then the elimination step. And then it repeats itself. Protonation, nucleophilic attack. Let's go like this. Protonation, and then elimination, okay? And it's just repetitive. And then once you have your final step here, which is the sulfuric acid taking its proton back, which it borrowed to us, your product will rearrange to look like this, which is the 1,3 conformation here. And you will add hydrogen fluoride for your spectroscopy result. So let's dive into details on each step. We're going to really focus on the, sorry about this, I typically have to, I struggle with this part. All right, so let's do this. Now I should be able to, oh, damn it. Let's just do this for now. All right, and then I can do this, and then I can go right. All right, cool. So we're going to go into steps very deeply. We are going to focus on these 4 steps mostly. Oh, sorry. We're going to focus on these 4 steps mostly, the first 4, because the rest of it is quite just a repeat. It's just repetitive of the same thing. So, our step 1 and our step 2. Our step 1 is protonation. Of course, this is an acid catalyst reaction, so it's gonna start with this catalyst igniting the flow of this whole reaction. You are welcome to also use a hydronium ion. This will be great. You might see other people drawing it like this. It's still basically, oh damn, it's still valid. Okay, there's a proton there. Don't draw it like that. Okay, so this is not a very basic group. However, this is acidic, like very much acidic, and as such, it is acidic enough that this mediocre, medium, basic group will attack it. The thing now is, we used to have, let me go to the next slide and I can show you better. We used to have a partially positive charge here on the carbonyl carbon, okay? But now after it was protonated, we now have a formal, full-on cationium positive charge on the hydroxyl there. This has resonance, so there will be times where this a positive charge will be on the carbonyl carbon, and that makes it so much more electrophilic than what this was, that this Pyrrole ring will attack it. Now you have to understand, this Pyrrole ring here is aromatic. Let's go to the next slide. Let's discuss the aromaticity of it. It's aromatic because these two electrons are part of the pi system. With other words, the sp2 orbital that runs around this ring in some current line. So it cannot attack it directly. It cannot do this. This does not exist, okay? Because these electron pairs is not isolated. They are, in fact, part of this whole ring. So this ring has too much electron density. It's got so much electron density that it eventually pushes it out, and then towards this very electrophilic carbonyl carbon. So if this wasn't electrophilic enough, then these electrons would not have left the ring. You need something very welcoming or inviting for that to happen, because it's giving up aromaticity, right? So another reason why this reaction works is because we have overlap, or at least a very nice alignment of the lower unoccupied molecular orbital, which is this acetone, and we have a very a high occupied molecular orbital, which is now higher, and as such these orbitals align, and the electron surplus from the HOMO gets transferred to the empty orbital of the LUMO, and that's why these two molecules align so perfectly for this reaction to move forward. There's another reason why this happens. It can be boring. It could have been an attack from here, but it's not. It's an attack going down, around, up, up. So another thing that we know about molecules is they do love the extra arrow pushing resonance structures. So you can take that into consideration when you draw this mechanism. This is the most arrows that can do arrow pushing for us, basically. So still on the first and second step, we're talking about aromatic, there's an aromatic ring, to an anti-aromatic ring. So if we have 6 pi electrons here, and if we push 2 out, then we've got 4 pi electrons. And that means it's anti-aromatic. But this anti-aromaticity is very short-lived, and very short temporarily. It will be replaced by aromaticity immediately afterwards. But let's have a look at our two molecules here. Let me just do this. We've got, this is an sp2 molecule, it's flat. This is a sp2 molecule, it's flat. All right, so we go from two flat molecules to one sp3 hybridized molecule. We've got 4 bonds on this carbon, and we've got 4 bonds on this carbon. And look here, there's some depth, there's some stereochemistry coming into play here. Still on the third step. Let's stay on the third step a little bit. So we're talking about the depth of this molecule, which is great because, in essence, what we want is for this molecule to go and build itself in the paper, into the paper, into the paper, into the paper, and then out of the paper, out of the paper, out of the paper, and then come here. All right? That's what we essentially want to form our microcyclic compound. So it's going to alternate between sp3 states back into sp2 states very quickly, immediately after the disruption of its aromaticity structure. Okay? Yeah. So still on the same step, we can discuss more. Here I just show you the form, how we want this macrocyclic ring to form. But moving on, we need to discuss why this proton is so acidic. So remember, we've got a very strong sulfuric acid competing to be deprotonated, right? But here we got this proton being deprotonated, and we don't see any sulfuric acid. Well, why? So first of all, we've got an electron withdrawing group here, which is nitrogen, and we got a hydrogen, an electron withdrawing group, here, oxygen. And we have some hydrogen bonding going on. However, this bond ain't all that strong because this nitrogen is more interested in getting electrons and it wants less protons, whereas this will want more protons because then it can form water, and water is a thermodynamically favored product. So in the end, the competition between these two molecules will be oxygen or the hydroxyl as the winner. And the fact that this is now a carbon that's got 4 bonds, it means that at this point it cannot go back into aromaticity here because we need a planar flat molecule to be sp2 hybridized for the aromaticity to restore itself. So it is going to remove itself and it's going to give up the electrons that's making this bond, and it's going to move down to make a double bond here, and then our other double bond there, and then that will go away basically. So let's look at step 4. Step 4, now we got a water molecule, and because water molecule is such a very favorable leaving group, we will see the nucleophilic attack happening from a second Pyrrole ring to go to this very tertiary carbon here to have water as a leaving group. So we can talk about things that's making this reaction move forward if we look at equilibrium and thermodynamic rules or laws. So one of the things that's moving this reaction forward, that makes this reaction foolproof, to be honest, is the removal of water. Water is our only byproduct in this reaction. Throughout this whole mechanism, only water will leave. There's no carbon skeleton that leaves. There's no other functional group that leaves. It's just water every time, okay? And then, of course, the fact that aromaticity gets restored over and over again is also a reason why this reaction will move forward and not like this. This doesn't happen. Okay, so moving on. Now we have another acidic proton, this time on this side of the ring, and as you can see, again, it is too bulky here and it's too busy to, there's too much bonds here for our planar aromaticity to be restored. So this needs to go away. These electrons should be given here to make a pi bond there. These will push up to go there, and we will get rid of that cation there. The same story. From here on, our reaction just stays the same. There's really nothing new here. It's just going to be a repeat of the previous steps over and over and over. But there are some things that we can take into consideration as this reaction moves on. We'll just go through all the steps. You can pause the video if I'm too quick, and you can draw it. So, once we have 3 Pyrrole rings, and they're all in aromatic formation, we can ask ourselves at this point, is this realistic? Isn't there a better way in which these 3 rings can rearrange itself to be less strained in terms of their bonds? Well, yes, there is. Basically, what you can do is you can flip the middle ring to point downwards, okay, because it's going to be more stable. It boils down to symmetry. Look here, if we have 3 rings and they're all facing upward, it's very unbalanced to what's going on down here. There's not even any functional groups here except for our aromatic ring, which is just down there, where we have like all these nitrogen, well, I can't say amine. Yeah, we've got all these amine groups here, and we got like them interacting with a carbonyl there. Whereas we have 4 molecules, which we will have eventually, and you draw a symmetrical line through them, they will be symmetrical. So therefore this structure will by nature flip the middle ring. Now, you don't have to worry about drawing that middle ring already. You can just take notice of it at this point in time. We will flip the middle ring, or every second ring rather, once the macrocyclic compound is going to close via an intramolecular nucleophilic attack. Alright? For now, you don't have to worry about flipping that ring. But if you want to flip the ring, you're welcome to flip the ring. Just then keep on drawing it that way, you know? So these steps are just all repetitive. Now I'm showing you we've got 4 rings, and now's the time to start flipping them. Once that aromaticity gets restored, you have to flip them. Now they have to be flipped. You cannot draw it any other way anymore, because if you do, it will not be a plausible mechanism. So this is the point where you have to flip them. As you can see, each ring basically goes through 4 transformations. It goes from being aromatic to being anti-aromatic to aromatic to anti-aromatic to back to aromaticity. So, I mean, that was 5 formations, but it goes through 4 steps in each transformation. With other words, it first gets anti-aromatic, then aromatic, then anti-aromatic, then aromatic. Each ring does that. There's 4, 4, 4. But this one, which is our first Pyrrole ring that we used, only did 2. And as such, it can still rearrange 2 more times to make sure that this ring can close on this side. Oh shit, there. So the other thing that you also need to take into consideration is that each, well, let me just first wipe this out and then draw with a thinner, okay, there we go. Each Pyrrole ring, let's draw this quickly. And they've got 2 hydrogens on the right and the left. Sure, they've got hydrogens here, they've got protons there, but we don't work with these. We just work with number 2 and with number 5. So each Pyrrole ring needs to give up at some point its number 2 proton and its number 5 proton. So far, the first ring here have only given up its number 5 proton. We still have the second proton here, so there is an implicit hydrogen there, and as such it's available for a transaction with some electrons to close the ring. So let's see how that happens. This is our final step. You see the ring is now closed, but we still have one ring that's now in anti-aromaticity, which means it has to go through one more rearrangement back to aromaticity. So we got our catalyst, our acid catalyst, claiming back that proton which it borrowed for this reaction, and the ring will restore its aromaticity, and then your product will look like this. Okay? So this is the 1,3 formation, and now you might have been instructed to add hydrogen fluoride to your product for spectroscopy results. You will probably do a UV vis, and you will probably do an HNMR. And there's many templates on the internet available for comparison on how these results should look. It's pretty distinguishable, it's pretty easy. You will not have a hard time with it. So I just show you here, this is how the formation looks when you add fluoride, which will act as an ion. Now, the question is, can we use other acids? Can we use other acids here? What about our, what about our sulfuric acid? That's been here this whole time, right? No. You cannot do that because this is too big to fit into this small cavity here, because this is the room that is available for this fluoride to be there. This molecule is wider than that, is more sterically hindered to fit in there. So it cannot fit in there. It needs to be a halogen small enough in an acidic form to become an ion to do this. All right, so hydrochloric acid can also work, but typically people do the fluoride version of it. So I think that is almost the end of this video. We're just going to look at what we learned today. So this is the full mechanism. You can pause the video and now you can draw this with confidence. Just note here that I have accidentally skipped a protonation step here. It's just this hydroxyl protonating itself with the hydrogen that is still available there. Okay, so this just goes to this. That's all this protonation step is, and then you can go on. So sorry about that. Moving on. All right, so here you will see that the reaction was basically just an exchange of groups. We gave away these two hydrogens, the number 2 and the number 5, and we used the acetone's oxygen, and that made water as our only leaving group, whereas the carbon skeleton of this acetone was the carbon skeleton used here, and the 1 pi bond here was used as the electrons to make the bond between the dimethyl carbon there. Okay, and that's basically the whole video. I'm just thanking you for watching this video, and if it was bearable, it doesn't have to be enjoyable. If it was bearable and helpful at the very least, please press that like button for me. I would really appreciate it. And good luck on your lab. It's really easy lab. You don't have to worry. Everything goes forward pretty easily.